Okay, so let's come to today's lecture. Okay, so in the last lecture, we have been talking about the Laplace transforms for derivatives. Okay, so very important formula that we obtained from the last lecture, saying that the Laplace transform, okay, so of the nth derivative of a function, right? So it will be equal to s to the power of n of the Laplace transform of the function minus s to the power of n minus 1, f of 0, okay, so minus s power n minus 2, f prime of 0 minus dot 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 minus f to the power of n minus 1 of 0. Okay, so this is a very important formula that helps us, okay, so that helps us to work out the differential equations using Laplace transforms. Okay, and we'll be introducing the inverse Laplace transforms because in one of our examples, so we were trying to solve this differential equation. Okay, so we were trying to solve this differential equation, and what we encountered there, so we try to solve this differential equation with the initial values, right? So with the initial values. And what we have encountered there is that by the Laplace transform, okay, so by the Laplace transform, it transforms the differential equation into an algebraic equation where you know the Laplace transform of y, okay? During this transformation method, initial values has been put into use, right? So it is very important that this problem is an initial value problem because the initial values is like the f0, f prime 0. These are going to correspond to the initial values. So indeed, these initial values, they're going to enter the Laplace transform as some constants from which you solve for the Laplace transform of y. Now the question is, if you know the Laplace transform of y, you don't know, you still need to know the y, even if you know the Laplace transform of y. It's not enough to just know the Laplace transform of y. So therefore, we have introduced this notion which we call the inverse Laplace transforms, right? So which we call inverse Laplace transform. Basically, you're inverting the Laplace transform. If you know this function, you're going to find its inverse, right? So that's going to be inverse Laplace transform. And in order to find inverse Laplace transforms, we have introduced a very important table. Okay, so we have introduced a very important table that I have guaranteed that you're going to see them on your exams. Okay, so when you go to the exams, they're going to give you this important table of Laplace transform, so-called table of Laplace transforms on your exam paper sheet. Okay, so it's usually attached to the last page of the exam paper sheet. Okay, so you can see that the left column are the functions, the right column are the Laplace transforms. Okay, so and some of them we have been introducing before and calculating before, like one is 1 over s, this one is the s minus a, right? So and sinuses of at, sinuses of bt, and the derivatives of f, etc. So in a certain sense, the rest of this chapter is about this table. So we're going to explain line by line of this table to make sure that every line of the table is being addressed. Okay, so that's going to be the topic for the rest of this chapter. Okay, so that's going to come back. Okay, so let's come back to our calculation last time. Okay, so last time from this differential equation, so basically from this differential equation we obtained, okay, so the differential equation, so the differential equation with initial value problem. So let's say last time, okay, so we have initial value problem, right? So we have initial value problem is given by this equation y double prime. Okay, so y double prime minus, okay, so minus the y prime, right? So minus the y prime minus the 2y is equal to 0. Okay, so minus the y prime minus the 2y is equal to 0, such that y0 is equal to 1 and y prime 0 is equal to 0. Okay, so that was the differential equation with initial values that we've been talking about last time. And we obtained this formula, okay? So we obtained this important formula, okay? So we obtained this important formula about the Laplace transform of y, okay? So about the Laplace transform of y, okay? So let me take it, okay? So we obtained such an important formula, okay? So about the Laplace transform of y, okay? So So that's what we obtained last time. Okay, so this is actually using these initial values, initial value problems. Okay, so using this formula about derivative transformation, you obtain this. Okay, so therefore, it is by our definition of the inverse Laplace transforms, it becomes legal to say that y is equal to the inverse Laplace transform of s minus 1 divided by s squared minus s minus 2. Is that good, February? Okay, so that's just the inverse Laplace transform of s minus 1 divided by s squared minus s minus 2. Okay, so that will be inverse Laplace. But this is not enough because you don't know what's exactly the inverse Laplace transform, but rather you have to calculate the inverse Laplace transform. So what's this object? Well, the idea the only idea, okay, so the only idea is to look at this table, okay, so the only idea that one can resort to is to look at this table, right? So on this table, what you are going to look at is this function s minus 1 over s squared minus s minus 2. Okay, so which line on this table is more appropriate to such a function? Okay, so which line on this table is more appropriate to such a function? Well, the denominator is s squared minus s. It's a quadratic. Okay, denominator is quadratic. So therefore, you must look for something quadratic, right? So the denominator is quadratic. So the quadratic ones are only this one, this one, this one, this one, 4, 5, 6, 7, maybe 9, 10, right? So and no else, right? So you must focus on these ones, right? So how do you make something similar to this? Well, this is a key idea. Okay, so one of the key ideas of this lecture. Okay, so the key idea, one of the key ideas of this lecture, these lectures and this course. Okay, so I would say for this course is that if you see a quadratic form. Okay, so if you see something quadratic, right? So you see something quadratic like this. You have two ways to do it. One way is to decompose it. The other way is to so-called complete in the square. So that means s squared minus s minus 2. Can you write it in the complete in the square? Well, you are not able to do so, right? So unless the b squared. So basically you have a s squared plus b s plus c. You want to decompose it, then you have two choices. One is that you want to write it as let's say a times s minus alpha and s minus beta, where alpha and beta are two real numbers. This is in the case when b squared minus 4ac is greater or equal than 0. But if the b squared minus 4ac is less than 0, you can only write it as a minus s minus s0 squared plus s1. Right, so that's kind of two ways to work with the quadratic formula. So this is very important for the rest of these lectures. And in this case, s squared minus s minus 2, the only way you can do it is to decompose it into s minus 2 and s plus 1. Is that good, family? Okay, so with this key idea at hand, you can see that the solution, okay, so the solution is actually given by y is the inverse Laplace transform, okay, so of s minus 1 divided by s minus 2 multiplied by s plus 1. So you're going to have exactly something like this. And for this formula, you then look back into the formula, right? So you then look back into the table of Laplace transform. So this is what you usually do on your exams. You have to go back and forth onto the table of Laplace transforms to find the answer that satisfies you. Okay, so that's kind of the thing. So you want to find the first order polynomials now because you have first order polynomials. Okay, so you have all these first order polynomials. So you want to find them, and therefore you want to look at the two, right? So you will not be bothered with these squares because none of them are going to make you satisfied. Right? So you're going to look at the two. But the 2 is just a first order polynomial on the denominator. It's not going to be a product of two first order polynomials, right? So if you think carefully, the second row, okay, so the second column of this table, there's nothing matching, okay? So there's nothing matching this inverse Laplace transform formula. So what should we do? Well, here we're going to introduce a very important method that you're going to use very often in your upcoming exams. Okay, so and you have already learned it in your calculus classes, but I'm afraid that many people have already forgot about it This is the so-called partial fraction decomposition. Okay, so this is the so-called partial fraction decomposition. Okay, so what is a partial fraction decomposition? Well, a partial fraction decomposition simply means that you can actually decompose a complicated fraction into a much simpler formula. Okay, so into a much simpler formula. So in order to do this, okay, so in order to do this, I have attached a few pages of remark notes by the end of this lecture note. Okay, so which is posted on Canvas. It's a general result on partial fraction decomposition. Okay, so what is a partial fraction decomposition? Well, partial fraction decompositions is going to deal with the type of functions f of x is equal to p of x divided by q of x, where p and q are polynomials. Okay, so P and Q are two polynomials. Okay, so you have P of X divided by Q of X, where the Q of X can be decomposed. Okay, so it can be decomposed into a formula like this. Okay, so let me take this formula. Okay, so the Q of X is kind of decomposed into a formula like this. Okay, so that's going to be your Q of X. Okay, so let's say your Q of X is going to be something. Okay, so something like this. Okay, so okay, so this is going to be your Q of X. Okay, so Q of X is going to be to have something like this. So what's this talking about? Well, these A's are the reals. So the AI's, the BI's, and the CI's are the real numbers. So that means the polynomial Q of X is going to have some roots. Okay, so the polynomial Q of X is going to have the roots A1 to AM with a multiplicity J1 up to JM. Okay, so that's the real roots. And in the case that you have complex conjugate roots, so we are going to have the result that BI square, BI, okay, so BI square minus 4 times CI is less than 0, which means that you are not able to decompose these quadratics into further polynomials. So you are not able to write this quadratic formula into the product of two first order polynomials, but you must live with the quadratics undecomposed. Is that good for everybody? Okay, so and this is indeed the case because for any polynomial, you are going to have either real roots or you are going to have complex conjugate roots. And in the complex conjugate case, you're not going to find real roots, but your quadratic formula is actually can be completing into the square, right? So if you're familiar with this algebra, and you have multiplicities J1, Jm, K1 up to Kn. Okay, so you have these multiplicities. Now the partial fraction decomposition simply says that you can decompose the f of x. Okay, so you can decompose the f of x into some partial fractions of this form. Okay, so you can decompose those partial fractions into the partial fractions of this form. Okay, so if let me take this form. Okay, so it is a kind of a little bit stunning formula, right? So it's like a little bit intimidating, but it's not so complicated as long as you get really familiar with it. Okay, so let me. So I would urge you not to be afraid, and I'm going to explain to you what it means. Okay, so this I'm going to explain to you what this formula actually is meaning. Okay, so that's going to be the scenario, right? So that's going to be the scenario. So let's put this formula there. Okay, so this is going to be okay. So this is not going to be the case. Okay, so this is going to be f of x. Okay, so that's going to be f of x. Okay, so that's going to be the f of x. Okay, so that's going to be so let me just one moment. Okay, so that's going to be the f of x. So how does this partial fraction decomposition go? Well, it's kind of clear from the first sum. Okay, so the p of x is a kind of a polynomial. Okay, so it's just a polynomial. And then what happens here is that your denominators, okay, so Remember, the q of x has been a denominator, so it has been a product of all these polynomials. Now its meaning in partial fractions is that each contributing product, okay, so each contributing factor is going to serve as one of the denominators of this problem, okay? So, but as long as you have the denominators, you're not going to just have the maximum power of this denominator, but you are going to exhaust the denominator from the first order power. So that means, for example, here, you're going to have p of x plus, so you have the first root is a1, okay? First the real root is a1, then you're going to have a, okay, so a I1 divided, okay, so let's say a11, okay, so a11 divided by x minus a1, but you're not going to immediately raise to the power of j1, you're just going to have the first order polynomial, and then a12 is going to raise it to x minus a1 to the power of square plus dot 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 plus a1, okay, so j1, okay, so and then it's x minus a1 to the power of j1. So basically, you're exhausting all the possible powers before you meet the maximum power j1. You're exhausting all the possible powers of the first contributing factor, x minus a1. Is that good for everybody? Okay, situation is the same thing as a2. So let's say a21 of x minus a2, right? So plus a22, okay, so of x minus a2 to the power of square plus dot dot dot, then the plus a2 j2, because the maximum power in terms of a2 is going to be j2 divided by x minus a2, right? So x minus a2 to the power of j2 plus dot dot dot. So you're going to kind of exhaust all these possible polynomials, first order polynomials, that are contributing as factors of this j1 to the power of jm, and you're finding all these possible powers. And similar thing happens for quadratic part, but for the quadratic part, you remember the numerator, okay, so the numerator always is one polynomial, is a polynomial of one order less than the denominator. So that means here the numerators are polynomials of first order and their powers. So the denominators are the polynomials of their first order polynomials and their powers. So that in this case, the numerator are going to be constants. But if the denominator are quadratics, the numerator has to be first order polynomial. So basically, you're going to have b, okay, so let's say b11, right? So b11 of x plus c11 divided by x squared plus b1 of x plus c1. That's the first order, but you're going to reach same thing. You're going to reach the maximum power is k1. So that means you're going to do b12 of x plus c12 divided by x squared plus b2 of x. So b1 of x plus c1, right? So let's say x squared plus b1 of x plus c1 to the power of square dot 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 plus b1 k1 of x plus c1 k1, right? So divided by x squared plus b of 1 of x plus c1 to the power of k1, because you want to reach the maximum power. Is that good for everybody? Okay, so and similar thing for the second and third, in each of these contributing factors in the quadratic part of this decomposition. Is that good for everybody? Okay, so this is exactly what we call it the partial fraction decompositions. Okay, so there are two things you must remember in this partial fraction decomposition. The first thing is that the numerators is one order less than the denominator. So denominator is the first order or maybe powers of first order. You're going to use constants. If denominators are quadratics, you can use the first order polynomials. Okay, and second thing is that you have to exhaust all the possible powers. It's not just the maximum power, but from the lowest power, you're going to raise to the maximum power. Is that good for everybody? Okay, so this is what we call the partial fraction decomposition. It means that the polynomial p of x divided by q of x, this ratio can be written into something like this. But how are you going to determine the ABC constants? Well, you can just use undetermined coefficients. Okay, so you can just use undetermined coefficients to find these constants. Okay, so this looks very complicated. Okay, so this looks very complicated. But let's apply. Okay, so let's apply the whole thing. Okay, so let's apply the whole thing to this polynomial. Okay, so s minus 1. So basically, I'm going to work with s minus 1 of s plus 2 multiplied by s, s plus 1. Okay, so and s minus 2, right? So that's let me work with this one. Well, this is a polynomial of this form, partial fraction decomposition, p of x divided by q of x. So how am I going to deal with it? Well, I don't have the quadratic parts, so therefore this one is just the first order polynomial, so it must be written as a1 divided by s minus 2 plus a2 divided by s plus 1, and these are just the first orders, so that if I exhaust the first orders, I will be enough, right? So just the first orders will be enough. You won't have to set. Remember, you're going to reach the maximum such power. Is that good for everybody? Okay, so you're going to reach the maximum such power. So as long as you have this, these constants, how we name them are not so important. So for example, it can be called A's and B's. Is that good for everybody? Now the poor problem is just to calculate the AB. How should we do that? Well, as I said, you can use the method of undetermined coefficients, so that this is A multiplied by S plus 1 plus B multiplied by S minus 2. So that's going to be A plus B multiplied by S plus A minus 2 times B divided by S minus 2 and S plus 1. Okay, so that's going to be S minus 2 and S plus 1. So you're going to have this. As long as you have this, your relation becomes A plus B is equal to 1, and A minus the 2 times B is equal to minus 1. So that's going to be the scenario from which you can solve for A and B. So basically, you're going to see that from the first equation, it just tells you that 2A plus 2B. Okay, so basically, let me make everything more neat. Okay, so that's 2A plus 2B is equal to 2, and A minus 2B. Okay, so the A minus 2B is equal to minus 1. Okay, so A minus 2B is minus 1. So that means 3 times A is equal to 1, which means that A is equal to 1/3. Is that good for everybody? Okay, so if A is equal to 1/3, B is equal to 2/3. Is that good for everybody? Because their sum has to be equal to 1. So in order to, with this at hand, you can see that, so finally, it tells us that S minus 1 divided by S minus 2 multiplied by S plus 1 has such a nice decomposition. It's 1 over 3 S minus 2 plus 2 over 3 1 over S plus 1. So that's going to be the decomposition. Okay, as long as you have this decomposition, the inverse Laplace transforms. Okay, so the inverse Laplace transforms can be applied to both sides of this solution, right? So that's this is the solution Y. I mean, the solution of the initial value problem is the inverse Laplace transform of this object, but this object has this nice partial fraction decomposition. Now, why do we want to use this partial fraction decomposition? Well, because it simplifies things, right? So remember, the Laplace transform has a relation that Laplace transform of alpha times f plus beta times g is equal to alpha of the Laplace transform of f plus beta Laplace transform of g, right? So the linearity of the Laplace transform is a very important property of these Laplace transforms. And indeed, if you have this, it means that the inverse Laplace transform is also linear. So alpha capital F plus beta capital G is going to be alpha, the inverse Laplace transform of F, plus beta, the inverse Laplace transform of G. So the inverse Laplace transform is also a linear operator, right? So that's both are linear. These are going to be very important formulas that you're going to rely on. Okay, so as long as you have the linearity of Laplace transform, you can see that you're able to pull these constants out. So that's going to be 1/3 of the inverse Laplace transform of S minus 2 plus 2/3 of the inverse Laplace transform of S plus 1. Is that good for everybody? Okay, so you can just decompose everything into the linear combinations. And now you can see that you have a much better scenario than before. Okay, so situation than before. Because the 1 over S minus 2 and 1 over S plus 1, one can find their Laplace transforms just from line 2 of this table. Because if you pick arbitrary A, then the 1 over S minus A, the inverse Laplace transform of this object, is going to be e to the power of at. Is that good for everybody? Okay, so that means you can see that the solution is 1/3 e to the power of 2t plus 2 over 3 e to the power of minus t. And that's going to be the solution. Is that good for everybody? Okay, so if we summarize, basically we started from this initial value problem. We have using this formula, okay, so using this formula for Laplace transform of derivatives, we have transformed everything, okay, so everything into the inverse Laplace transform of a quadratic, rational polynomial. And these ratios, in order to deal with ratios, first of all, we observe that denominator are decomposable into the first order powers, and we have been introducing the partial fraction decomposition to write this denominator into this the whole thing into the partial fraction decomposition. And using the partial fraction decomposition, as well as the linearity property of Laplace transform, we're able to find the inverse Laplace transforms by tracing the table. Okay, so we reduced everything to something that you can really trace on the table. And as long as you trace it on the table, you have the solution. Is 1/3 e to the power 2t, 2/3 e to the power minus t. Okay. Here, as a homework exercise, you can use the characteristic method to solve this equation, and you're going to see that you're going to reach the same answer. Is that good for everybody? Okay, so this is kind of the power of Laplace transforms. You can see that we have never been calculating these two constants, 1/3 and 2/3. They pop out immediately in the partial fraction decomposition, simply because we have already taken care of the initial conditions in our decomposition formula. Is that good for everybody? Okay, so this is a nice example how Laplace transforms is helping you to solve initial value problems. Okay, so this is a nice example that shows how Laplace transforms is helping you to calculate initial value problems. Is that good for everybody? Okay. So now let's some exercises. Let's try to first practice how to find the inverse Laplace transforms on the table. Okay, so now if you look at the table, you can see that the first column are the functions, second column are the Laplace transforms. So it can help you to do forward Laplace transforms. And if you want inverse Laplace transform, you should focus on the second column. Okay, so let's say forget about the index column. You should focus on the second column and find if there is some functions similar to what happens on the second column, and then you transform back. Is that good for everybody? Okay, so this is going to be very important for your future examinations. Okay, so let me show you some examples. For example, can you find the inverse Laplace transform 4/s² plus 9? Okay, so let's say I want to find the inverse Laplace transform of 4/s² plus 9. So what should I do? Well, I should look at the second column of this table. Okay, so and which function looks pretty much like 4/s² plus 9? Well, s² plus 9, so you can immediately see that somehow 4 and 5 are more similar, right? So this because it's s² plus some b². But if you want 9, b should be equal to 3. So basically, you can see that this is the inverse Laplace transform of 4/s² plus 3². Is that good for everybody? Okay, ideally, you're going to have what? Well, ideally, you are able to calculate 3/s² plus 3², because if you look at the table, right, so if you look at the table, it's b/s² plus b², or it is s/s² plus b². So you want the b, and the b now is equal to 3, so you want a 3. But it doesn't quite matter. You can say that this is 4/3 multiplied by 3. But because the Laplace transform is linear operation, the 4/3 can actually be pulled out of this Laplace transform without affecting the result of the Laplace transform, inverse Laplace transform, because the inverse Laplace transform is also linear. So you can actually do this. Now, as long as you have this is 4/3, the inverse Laplace transform of this b/s² plus b² is a sine bt, right? So it's a sine bt. So therefore, you're going to just have sinuses of 3 times t. Is that good for everybody? Okay, so you just can have sinus 3 times t. So this is how you use the inverse, the Laplace transform table to find the inverse Laplace transforms. Okay, so they're going to be very important for your future exams because you should be able to find these inverse Laplace transforms on an exam just by tracing the table. Okay, so that's why I'm showing you how this is being practiced. Is that good for everybody? Okay, let's practice one more exercise. Okay, so for example, here, can you find the inverse Laplace transform of this function, 2s/s² minus 9? Okay, so now we want to find, okay, so let's say we want to find the inverse Laplace transform of 2s/s² minus 9. So what should I do? Well, again, you should look at the table. Okay, so which one has a denominator something like s squared minus something? Well, it must be either 6 or 7, right? So it's s squared minus b squared, which means that b should actually be equal to 3, right? So let's first realize that they can be written as 2 times s divided by s squared minus 3 squared. Is that going family? Okay, so you can write everything like this. Now, as long as the things are like this, you can see that your numerator is s. So indeed, number 6 is not going to work, but line 7 is going to work because you have an s on a numerator. So that means, as before, you can pull the 2 out. So that's 2 times inverse Laplace transform of s over s squared plus 3 squared. So that will be good, well, because you can choose the b to be equal to 3, and you use this formula. So that's cosine h, right? So this is the cosine h of 3t. And what is the cosine? So yeah, cosine h of 3t. And what is the cosine h? Well, cosine h, as I said last time, hyperbolic cosine. So it's a e power of 3t plus e power of minus 3t divided by 2. So it's just e power 3t plus e power minus 3t. Is that good for everybody? Okay, so this is how you find the inverse Laplace transform of this second table. Okay, so that's now the problem for this inverse Laplace transforms is that sometimes it has to be combined with the partial fraction decomposition that we just introduced in this lecture. Because from time to time you're going to see formulas. Okay, so you're going to see formulas that are not necessarily can be reduced directly to something on the table, but you have to do a partial fraction decomposition first before you can reduce everything to the table. Okay, so let's look at the following exercise. Can you find the inverse Laplace transform of 5s plus 1 s squared minus 2s plus 3? Okay, so I want to find the inverse Laplace transform of 5s minus 1. Okay, so s squared plus 2s plus 3. Okay, so let me say if I make every coefficient correct. Okay, so s squared minus 2s plus 3, 5s plus 1. Okay, so it's a 5s plus 1, s squared minus 2s plus 3. Okay, so I want to find the inverse Laplace transform of this object. Now, how do I do it? Well, the first thing is that you can look directly at the table, but soon you will realize that none of these formulas are going to exactly match what happens to what you want to calculate, 5s plus 1 divided by s squared minus 2s plus 3. So they are not going to exactly match. And therefore, what you should do? Well, as I said at the beginning of this lecture, the very important key idea is that whenever you see a square, you either decompose it or you complete the square, right? So can you decompose this one? So s squared minus 2s plus 3, are you able to write it as s minus alpha multiplied by s minus beta? Well, this is not possible because b squared is 2 minus 4 times ac is going to be less than 0. Is that good family? Okay, so that's the discriminant is less than 0. You're not able to do the decomposition. So therefore, you must complete the square. As long as you complete the square, you're going to see that this is s minus 1 square plus 1 square, so plus 2. Is that good family? Okay, so the completing the square is good. It's going to tell you that L inverse of 5 times s plus 1 of s minus 1 square plus, I'm going to write this as square root of 2 square. Why write something like this? Because if according to this formula, what you would like to see is s minus a squared plus b squared. So you have s minus a squared plus b squared. Is that good family? So that means b is the square root of 2 and a is actually equal to 1. Is that good family? Okay. What about the numerator? Well, the numerator is hard to deal with because the numerator, it looks like none of these two. Okay, so now we're focusing our eyes at line 9 and line 10. Right? But even if you focus on 9 and 10, none of them matches because it's b or s minus a. You're not going to have really b or s minus a. You're going to have this 5s plus 1. Is that good for everybody? Okay, so that's going to kind of give you some trouble, but it doesn't matter because you want s minus a. So let's do it gradually. Okay, so let's do it gradually. So that means you have a 5. So 5 doesn't matter. So let me write s minus 1. Then it's going to plus 5 and then plus 1. So it's going to plus 6 and s minus 1 square plus the square root of 2 square. You're going to have this. Now s minus 1 multiplied by 5. And then I will have a b, right? So that's either s minus 1 Okay, so it's Sn minus 1 or the b, and the b square is equal to b is the square root of 2. So it's better to write a b, but then 6 is going to be replaced by 6 over the square root of 2 in order not to make any errors. And because of linearity, this can be written as the inverse Laplace transform of s minus 1 of s minus 1 square plus the square root of 2 square, and then plus 6 over the square root of 2, the inverse Laplace transform of square root of 2 s minus 1 square plus the square root of 2 square. So you're going to have something like this. And as long as you have this, you can see that you come back to exactly match this formula, where it is s minus 1 is a is 1, so it's e power at of cosinuses of bt. So that's going to be e power of at of cosinuses of bt square root of 2 of t plus 6 over square root of 2 is actually equal to what? Well, it is equal to 3 times the square root of 2. Is that good for everybody? What about this one? Well, this is like b, okay, b over s minus a squared plus b squared. So again, it's e power with a sign. So that's e power of t sinuses of square root of 2 of t. And that's going to be your inverse Laplace transforms. Is that good for everybody? Okay, so that means sometimes you have to do a little bit more algebra in order to reach a satisfactory answer. Okay, so in order to reach a satisfactory answer. What about this one? Well, for this one, you have to start to do partial fractions. Okay, so for this one, you have to start to do partial fractions. Okay, so let me show you one example. Okay, so let's say I want to find the inverse Laplace transform. Okay, so I want to find the inverse Laplace transform of this formula. Okay, so I want to find the inverse Laplace transform of this formula, right? So let's say, what's the inverse Laplace transform of this object? Now, in order to do this, you can just use this partial fraction. So that means s over s minus 2 multiplied by s minus 3 and s minus 6, right? So you're going to have this. Now you want to use a partial fractions, so that means you would like to write this one as, so the denominators are first order polynomials, they're just multiplied together. So according to our partial fraction, you can just work with s minus 2 plus b over s minus 3 plus c over s minus 6. And indeed, you just want to recover the constants a, b, c. So that kind of results in quite a lot of calculation, which is typical on your exams. Okay, so you have to be very patient in order to calculate these calculations. So basically, this one is actually equal to what? It's s minus 2 multiplied by s minus 3 multiplied by s minus 6. Then you're going to have a multiplied by s minus 3, s minus 6, plus b multiplied by s minus 2, s minus 6, plus c multiplied by s minus 2, s minus 3. So that's going to be this situation. But then you're going to decompose everything. You can see that s squared minus 9 times s plus 18, right? So plus b times s squared minus 8 times s plus 12 plus c multiplied by, okay, so plus c multiplied by s squared minus 5 times s plus 6, right? So that's you have the calculation is a little bit tedious, but you can actually do it if you're patient enough. So that's going to give you what? It's going to give you a plus b plus c multiplied by s squared, right? So, and then about s, you're going to have plus, okay, so plus what? Minus 9 times a minus 8 times b minus 5 times c multiplied by s. And then plus the constant term is 18 times a plus 12 times b plus 6 times c. So you have this term. And then it divided by the denominator is s minus 2, s minus 3, and s minus 6. Is that good for everybody? Okay, so that's going to be the scenario. Okay, so that's going to be the scenario. As long as you have this, you can see that a plus b plus c should be equal to 0 because you don't have s squared term here. And you have minus 9 times a minus 8 times b minus 5 times c is equal to 1. And 18 times a, okay, so plus 12 times b plus 6 times c is equal to 0. So that's going to be the formula that you really have here. Now, how do you calculate this ABC? Well, in order to calculate this ABC, you have to solve everything from the 3 by 3 linear system of equations. Okay, 3 by 3 linear system of equations. And indeed, you can do so if you're patient enough. Let me say how to do it. Well, let's multiply this equation by 2. So that's minus 18 times A, 16 times B, 10 times C is equal to 2. If you use this equation to add this equation, you're going to see that minus 4 times B, right? So minus 4 times B, and then minus 4 times C is equal to 2. So that's basically, it tells you that B plus C is equal to 1/2. Is that good for everybody? Okay, so you're going to have such a nice formula, right? So, and if B plus C equal to 1/2, then you can see that from the first equation, A is just equal to minus 1/2. So A is found. And once A is found, you can easily find B and C, right? So you can easily find B and C, because if A is found, you just need one equation. Let's say I will use this equation. Okay, so that means that if A is minus 1/2, it's just minus 9 plus 12 times B plus 6 times C is equal to 0, which is simply saying that you can divide everything by 3. So 4 times B plus 2 times C, right? So is equal to 3. So that's going to be this, right? So, and then if B plus C is 1/2, you can see that 2B plus 2C is equal to 1. You can use this equation, subtracting this one. So basically, finally, okay, so now finally, you get 2 times B is equal to 2. So B is equal to 1, and then C is equal to minus 1/2. Is that good for everybody? Right? So that's going to be kind of very simple. You find A, B, C. A is equal to minus 1/2. So that means A can be equal to minus 1/2, right? So, and then you can see that B is equal to 1. Okay, so B is equal to 1, right? So, and C is equal to minus 1/2. So C is equal to minus 1/2. You have the coefficients here. Is that good for everybody? Okay, so as long as you have this, it means that you're just calculating the inverse Laplace transform of minus 1/2 s minus 2 plus 1 over s minus 3 minus 1/2. Okay, so minus 1/2 of s minus 6. And then you can easily calculate the inverse Laplace transforms from the table, because you're going to use line 2. Okay, s minus a, 1 over s minus a is e to the power of at. So that's going to be minus 1/2 e to the power of 2t plus e to the power of 3t. Okay, so plus e to the power of 3t, right? So e to the power of 3t minus 1/2 e to the power of 6 times t. Is that good for everybody? Okay, so this is kind of sometimes these partial fraction decompositions, they really take time when you do these calculations. Okay, so when you do these calculations, these partial fraction decompositions are going to be really taking time. Okay, so are going to be really taking time when you do these calculations. Is that good for everybody? Okay, so that's going to be the scenario that you're going to kind of quickly meet. Okay, so when you are really on these exams. Okay, when you are really on these exams. Okay, so now let me finish today's lecture by considering one last problem. Is about an initial value problem. Okay, so it's one last problem is about an initial value problem. Okay, so the initial value problem that we'll be interested in is to calculate this differential equation. Okay, so is to calculate this differential equation. Okay, so it's to calculate this differential equation. Okay, so okay, so you're going to calculate this differential equation. Okay, so let me put it here. Okay, so and so we're going to kind of work out this differential equation. Okay, so this one is just one moment. Okay, so we're going to work this one out. Okay, so okay, so we're going to work out this. This is a fourth order differential equation. Y to the power of 4, fourth derivative minus 4 times y is equal to 0 with all these initial conditions. Okay, so how are we going to work out this differential equation? Well, we're going to apply the Laplace transform on both sides of this equation. So 4 times y is equal to right hand side is Laplace transform is 0. Now you realize that Laplace transform of y fourth derivative, remember it's s to the power 4, Laplace transform of y minus s to the power 3, y of 0 minus s to the power 2, y prime of 0 minus s, y double prime of 0 minus y triple prime of 0. Is that good, family? Okay. Now, by initial values, it means that you can actually use these initial values here that are just given to you. So that means this S4 Laplace transform of y minus y of 0 is 1. So that's S cubic, right? So y of 0 is 1. Now, y prime of 0 is 0. You don't have anything here. Y double prime is minus 2. So that's plus 2 times s. Y triple prime is 0. So you're going to have something like this. So that means you're going to see that the equation now becomes s to the power 4 Laplace transform of y minus s cubic. Okay, so plus 2 times s, and then minus 4 times the Laplace transform of y is going to be equal to 0. Is that good for everybody? Okay, so what does it give you? Well, it gives you that Laplace transform of y is s cubic minus 2 times s divided by s to the power 4 minus 4. So this can be written as s squared minus 2 multiplied divided by s squared plus 2, right? So multiplied by s squared minus 2, and therefore the s squared minus 2 is going to cancel. So that's going to be s over s squared plus 2. Is that good for everybody? Okay. As long as you have this, you know that y is equal to the inverse Laplace transform of s over s squared plus 2. I'm going to write it as square root of 2 squared. Why I do this? Because just on the table, you can see that s squared plus b squared is what you really want, right? So s squared plus 2 can be written as s squared plus square root of 2 squared. And you have an s on the numerator. You have an s on the numerator. It's going to kind of cosinuses. So that's going to give you the inverse Laplace transform is just the cosinuses of square root of 2t. And this is indeed the answer to this differential equation, just very quickly, right? So you can see that applying the Laplace transforms gives you a very quick answer to this differential equation. You can use the characteristics, but then you're going to be working with the fourth order polynomial, and you're going to solve for 4 constants for the fundamental solutions. But for the Laplace transform method, it becomes very fast. You can just apply the Laplace transform, you find the Laplace transform, and you do an inverse Laplace transform, you trace the table, that's going to give you a solution. So this is a very simple and very straightforward, as well as very powerful, okay? So as well as very powerful method. That's kind of very interesting for the rest of these lectures. Is that good for everybody? Okay, so that's what I want to say for today's lecture. Let's come back on the next lecture, and we're going to continue with Laplace transforms. Okay, see you in the next lecture.